I am Vaibhav Srivastav from Vaibhav E-Learning Academy, and today we are going to start a topic that is very common, that is logarithm. Now, the topic logarithm is covered in almost each and every subject. Logarithm can be used in mathematics, physics, in physical chemistry, and in many more branches. So, logarithm is one of the most important and basic fundamental concept of mathematics. In today's video, we will be discussing about the exponents required, because before learning the logarithm, we have to learn some important exponents which might be required for the logarithm. Then we'll be learning about what is logarithm. Then we'll be learning about antilog. Antilog, that is actually a very easier topic. It is just the opposite of logarithm, as the name suggests. Then we'll be learning about Euler's number. Now, Euler's number or Napier's constant is a number which has a definite value, just like pi, and not a definite value. It is an irrational number which has some value. Now we'll be discussing about this Euler's number because we use that in logarithm. How we'll be looking at it in the video. Then we'll be discussing about the properties of logarithm. There are several properties of logarithm, like the addition, the multiplication, and then we'll be discussing about the log base 1, base 0 and LCM, and then we'll also be discussing about the derivations of those main properties, like the multiplication and division. And then we have the questions over here. So we'll be practicing some question. This won't be done at the last, but it will be done alongside with all the important concepts. So now let us start. Before moving on to the topic of logarithm, we need to understand what an exponent is and what is the required exponents for logarithm. Now, starting with exponent. Exponent. Now, this concept of exponent is written or understood in many different languages. Exponent can also be written as power or index. Now, we all know what the meaning of power is. The meaning of power, it means that how many times you are multiplying that same number. Suppose, and actually exponent is in the form of a power x, where a is any number. I am talking generally about the powers, and x is the exponent. Now, usually when we talk about exponents required for logarithms, then we will say that a should be greater than 0 and a should not be equal to 1. These are the main conditions. Now, why are these conditions? We will be learning them when we learn about logarithm. Now, this is the main format of representing an exponent. Now, this a is actually called as base, and this x is called as the power or the exponent. Now, what does this represent? It represents multiplying a with itself x amount of times. A into a up to x times. This is the meaning of an exponent. Now, how will you relate exponents with logarithms? Before moving on to the logarithm, we need to understand what is logarithm. So, logarithm is nothing but a function of mathematics. So let me write that down. Now, what is logarithm? It is a function of maths. Function of mathematics. Now, before moving on, what is the meaning of function? Now, let us take an example of a switch. Or let us have two switches. What switch? This is an electrical switch. Suppose this switch turns on a fan and this switch turns on a tube light. Now, if you press this button, the fan turns on. If you press this button, the tube light turns on. Now, this is called as mapping. It means you are relating this with the thing. If you press this button, it performs a particular function. And what is a function? The function is to turn on the fan. Now, if you talk about the topic of function, function is actually a very big topic in mathematics, but we'll be learning only a little bit required, and we'll be learning what is the function. So, function means when you use this logarithm, for example, when you apply the logarithm, you will get one specified value. Or if you have the specified value, then you have the logarithm to reach that specified value. So, it means that if there is a switch, you can turn on only one thing with that switch. If you have a switch which turns on both fan and tube light, then that is not a function. It is actually not a function. This topic will be learned in detail in the topic of relations and functions, but here we need to understand that logarithm is nothing but a function in mathematics. Now we have to learn about the basic representation. The representation of logarithm goes like this: log of a to the base b is equals to c. This is actually called the representation of logarithm. And how do we say this? We say this as log of a to the base b is c. Now here this a and b are the terms. And how do you get what is a, what is b? Now we have learned about the topic of exponents. In exponents, let us take one example of 3 to the power 2. Now 3 to the power 2 is written as 9. Now how can we represent this 3 to the power of 2, which is equals to 9, in the form of log a? Now basically we know that logarithm and exponents are related. How are they related? This relation is actually nothing but logarithm. Now if I try to write this relation in this form, we will get at log 9 to the base 3 is equals to 2. Now if you try to relate these both concepts, we will find that c is 2. In this equation, what is 2? 2 is nothing but the power. Then c is the power. Then we have 9. What is 9 here? The 9 is the answer to the question. And what is 3? 3 is the base. Log of a number to the base b gives us c. Now this is as a power we have here as 9, right? So 3 square is equals to 9. Then if I try to take the log of 9 to the base 3, then it will give me 2. Now what do we understand by this? This logarithm function tells us that we have this answer 9 and we have the base as 3. How many times should I multiply the base to itself so that I get the answer as 9? So answer is 2. It means if I multiply 3 into itself 2 times, then I will get the answer as 9. So this is what logarithm actually tells us. Let us take one more example. Let us take, we have log of 16 to the base of 4. Now what will we get? It as the answer. Now what do we understand this? What power of 4 gives me 16? This is the actual question which this statement asks. Now what power of 4 gives me 16? 4 power x is equals to 16, and that x is nothing but c. And what is x? We know that it is 2. Then log of 16 to the base 4 is nothing but 2. How can we represent this in the form of exponents? Representing this in the form of exponent can be as 4 square is equals to 16. Now this is the relation between logarithm and the exponent, that log 4 square is equals to 16 and log of 16 to the base 4 is 2. So if you multiply 4 2 times to itself, then you will get the answer as 16. This was the basic meaning of log. Now talking about anti-log. What is anti-log? The same thing which we did right now is called as anti-log. Anti-log. Now what did we do over here? We have, suppose 3 square is equals to 9. How did we represent this? We represented this as log of 9 to the base 3 is equals to 2. Now representation of an exponent in the terms of logarithm is called log, and representation of a logarithm in the terms of exponent is called as anti-log. So what did we do? We removed the log term. Now we are able to represent the logarithm terms in the form of exponential terms. This process is called as anti-log. And when we have to convert the logarithmic values, or not the logarithmic, the exponential values into the logarithmic values, then that is called as log. Now before moving on to the Euler's number, or before moving on to the main basic types, we need to understand about what is the logarithm's base. Now there are two types of logarithm. One is called as natural log and one is called as common log. What is the difference between a natural log and a common log? Now we have log of a to the base b is equals to c. Now this base b can be variable for many questions, but the base b is usually specified. Now this base b can be either 10 or e. So we usually say log of, suppose 2 to the base 10 is equals to, let us say, x. So now this is called as the base 10. Now this b can be a base 10. Now we have a natural log and a common log. The common logarithm is in the form of log to the base 10. That is the common log. And what is the natural log? Natural log is nothing but log to the base e. Common log is nothing but log to the base 10, and natural log is nothing but log to the base e. This is called as log dot n, or we can usually say this as ln. So that whenever we hear the term ln, or whenever we present or express the term ln, we say this as log of x to the base of e. Suppose ln x. Now this was common log and natural log. Whenever we learn about logarithms, there are some values of logarithms which are required for general chemistry, general mathematics, and those are nothing but the values of log. Suppose we have log, and when we talk about log, that is log to the base 10. We need to learn the values of log 1 to log 9. The value of log 1 is 1, log 2 is 0.3, log 3 is 0.48, log 4 is 0.6, log 5 is 0.7, log 6 is 0.76, log 7 is 0.84, then we have log 8 as 0.9, we have log 9 as 0.96, and we have log 10 as 1. Now these are the values of logarithm. For now we just know that the log 2 is 0.3 and log 3 is 0.48. But what is the meaning? As we said, when we are talking about log, this is the base 10. So let us see log base 10 2 is equals to 0.3. From the basic definition, what do we mean? What power of 10 gives us 2? Then we can say 10 to the power 0.3 gives us 2. So this is the meaning of logarithm. We use these logarithms in many mathematics and physics problems, but more than this, even we have the requirement of the concept of ln. Now what is the concept of ln? The concept of ln is such that ln x, which means that log of x to the base e. We usually will have the values in the terms of ln of x. We need to convert ln of x into log of x to the base 10. To convert ln into log, we need to multiply this into 2.303. So ln x is equals to 2.303 of log 10, log to the base 10 x. For now, we know these are the values of the logarithm. But how did we get 0.4 is equals to 0.6? How did we get 0.6 is equals to 0.76? 0.8 log 8 is equals to 0.9. Log 10 is equals to 1. Log 9 is equals to 0.96. These all logs can be derived. The most important and the logarithms which we actually need to remember is log 1, log 2, log 3 and log 5. These 4 are very important, and from this 4 we can derive all the logarithms, and also 7. Actually the 7 can also, we can ignore the 7 because log 7 is just the opposite of log 3. Log 3 is 0.48 and log 7 is 0.84. That log 3 and log 7 are opposite of each other. Now we are going to move on to a very interesting concept, that is the concept of E. So for now we are leaving this topic hanging. We need to do some questions also, and we need to understand. But the main questions will arise after we complete the properties, because after the properties of logarithm, we will understand how did we get these values. Till now, whatever we have learned is raw. What is the meaning of raw? It means that we do not have any starting of the thread of this topic. That we just randomly started this topic. What did we do till now? We just learned what is the meaning of logarithm, what is the meaning of anti-log, how can we express exponents into logarithm, and we learned about some basic log values. Till now we have left this topic 100% hanging. We don't know how to complete this topic. To complete this topic, we need to learn about a very important thing that is called as properties of logarithms. Because after learning the properties of logarithm, we can be able to derive all these formulas, all these numbers, all these values. Before moving on to that, we are going to discuss about a very interesting topic, that is e. Now what is e? We are saying log x. It means that log of x to the base e. Now what is e? How did this e come, and what is the significance of e? We'll be discussing that. So let us see. So now let us discuss about what is the term e. In natural logarithm, we use this term as log of x to the base e. Now what is this e? This e is termed as Euler's number. Euler was a scientist, and then we also call this as Napier's constant. Now this Euler's number or the Napier's constant can be calculated by using the concept of a compound interest. Now the formula of compound interest is A is equals to P into 1 plus R by n to the power of nt. This is the formula for compound interest, where P is the principal amount, that is the amount which you pay, R is the rate of interest, n is the frequency at which the interest is calculated, and t is the duration for which you are getting the loan or the borrowing, whatever it is. So now the concept of the Euler's number, the concept of e, starts from a matter of fact that we have been talking about exponents and we have been talking about logarithms. So let us take there is a value of 3. Now when you put a power on it, x, this number changes, and mostly if you apply the correct logarithm or if you apply the correct powers, it increases. This is called a growth. Or when you increase the value of x, if you increase the value of x to like 1000, 10,000, then that growth is called as exponential growth. Now we will be talking about a thought project or a thought concept where we take an example of a bank. Let that bank be an X bank. Now this bank gives you 100% interest. Let us suppose an ideal bank which gives you 100% interest on your deposits. So if I deposited suppose 100 rupee, after 1 year I will get 200 rupee. So it gives us 100% of interest. So as we know, P is principal, R is rate of interest, and is the frequency. Now we will start the idea by taking a simple principal amount to be rupee 1 rupee. So I deposit 1 rupee in a bank account and let the rate of interest be 100. So if it is 100%, then 100 by 100, that is equal to 1. And let the time period be 1 year. And the n over here, because the banks or wherever you have to calculate compound interest, we calculate it in the number of time periods or intervals. Suppose we want to calculate it for 1 year directly, so that will not be compounded, simple interest. So here it will be 1. When you put these values, let us say we have to calculate the interest for 1 year. Then we will get A is equals to P gets 1, R is 1, so it will be 1 plus 1 by 1 to the power 1. That is 1 plus 1, 2. Very basic, very common, that if you have 1 rupee for 1 year at a rate of 100% interest, then you will get 2 rupee at the end of the year. That is correct. Then let us suppose they compound the same. Now see, if you get for 1 year you are getting suppose 100%. Can we divide this into 6 months and 6 months? You are compounding it at 6 months. It means that you will get 2 intervals over here. So we have 6 months. Now it means that they are calculating the compound interest at 6 months. Then the time still remains 1 year, but here the n becomes 2. Why? Because the time is 1 year, but we are calculating the compound interest at 2 intervals. Then what happens? We get A is equals to 1 plus 1 by 2 to the power nt, right? So this becomes 2. So this is 3 by 2 whole square. So this is one 9 by 4, that is equals to 2.25. Now here something interesting can be noticed. If you have the same 100% interest at just once in a year, then you get 2 rupee. But when you compound it at 6 months, then you will get 2.25 rupee. So you get an additional 0.25, that is 10%. 10% more than this value. That is a very good growth. Now suppose instead of doing it for every 6 months, let us suppose they compound it every month. The bank compounds your amount, the bank compounds your deposit every month. Then this will become 12 months. Then A becomes 1 plus, why am I not writing P? Because P is the principal value, that is 1. So A becomes 1 plus 1 by n value, here n value becomes 12. 12 to the power 12. This value after calculating we will get 2.61 something. This will be the value for the when your 1 rupee is compounded every month for 1 year. Same, it is 100%, same the duration is 1 year, but we are compounding it multiple times. Every month we are calculating the same interest. Then after 12 months, let us suppose the bank calculates or it generates the compound every single day for 1 day. So each day it is calculating the compound interest for that same 1 rupee. Now here A becomes 1 plus 1 by, for 1 day per year. So since the number of terms is 1 year, the n becomes 365. This becomes 365 to the power of 365. This value is hard to calculate normally, but if you calculate the value, we will get it as 2.714 something. This value is very close to the value of E. I'll tell you more about it in a moment, but here we have the value for 1 day. Now till here, what did we understand? We understand that if you take just these two examples, here we have 2 and here we have 2.25. When we increase the number of times to be compounded, so here we compounded it once per year, now here we are compounding it twice per year, then we get an increased gain of 10%, that is 0.25. When I increase it to 12, then still I get a gain from 2.25 to 2.61, that is almost a 0.4, almost 0.4 gain we are having. Now when I am increasing the number of terms from 12 to 365, that is a very large jump. But if you see the gap between this is not less than 0.10%. So 0.10. Now this is a very interesting concept over here. We were increasing the number till 12, then we saw that the growth was good. We are having a good and considerable growth. But after increasing it from 12 to 365, the growth slowed down. Now what mathematicians did, or what Euler did, that instead of taking any amount as base, now forget the concept of bank or interest or whatever it is, when we take the value of A to be 1 plus 1 by infinity, to the power infinity. Why did we do that? Because we want to find till what limit can we increase the value of 2. Like Euler wanted to find out that if I give 1 rupee, suppose the thought experiment, that if I give 1 rupee to a bank and if I try to compound it like into an infinitely large amount of periods, then what is the maximum amount that I can get in 1 year? So infinity is not an actual concept, because in mathematics infinity is nothing but an imaginary concept. Let us take a very large number, suppose 10 to the power 5 or 6, 10 to the power 5. Then this answer comes 2.718 or so. Now did you see the difference over here? We increased the number of times for compound from 365 to 10 to the power 5. That is a very enormous jump. But here we expected an enormous jump because even we increased the power. But the actual value increases by 0.004. This concept is actually called as the concept of Euler, or this is called as the concept of Napier. So from here we took the following thought. We thought that if we take an compound interest A for 1 rupee for 1 year and we compound it infinite times, then we get E rupees. Or we get the amount of E. This E is nothing but an irrational number. This lies between 2.72 and 2.71. This is the concept of E, or the Euler's number. and we use this concept in the topics of logarithms in the natural ones. So I hope you understand what is the Euler's number. Let us move on to the properties of logarithms. Let us move on to the properties of logarithm. In the starting of the video, we took the exponents. We took exponents, or we took the actual value of log as log of b to the base a is equals to c, and we took the value of exponents as a power x is equals to, suppose, the value c. Now this is the value which we are having. Now if you want to write it in terms of this, then we will have a to the power of c is equals to b. This is the value which we get. Now here what we said was the value of a should be greater than 0 and the value of a should not be equal to 1. These were the conditions which we gave. These conditions were given to define the value of logarithm, or we can say log of a to the base b. So now the question is, why did we take a to be greater than 0? Suppose let us take a as 0. When we are taking a as 0, we will get a power x as a value c. If you take 0 power, let us say 1, we will get as 0. 0 power 3, 0. 0 power 9, 0. If you try to write this in the form of logarithm, we will get it as log of 0 to the base 0 is equals to what? Now here log of 0 to the base 0. Now here answer according to this. See, actually this term is not defined, or there is another argument that log of 0 by 0. So here we are supposing log of 0 to the base 0 is 1. How? We are taking this value. Okay, now let us try to take this. Again we get log of 0 to the base 0 is equals to 3 here. How? Log of 0 to the base 0 is equals to 3. How many times 0 should be multiplied to itself to get 0? And from here we should get it as 3. Now I think you understand what the problem over here is. Let us take another value. Suppose this is minus 9. So log of 0 to the base 0 gives us minus 9 according to this. Now here we get a confusion. This log of 0 to the 0 gives 1. Log of 0 to the base 0 gives 3, and it also gives minus 9. In the starting we spoke about function. Function means that one output is given by one input. Now here one input has multiple outputs. So when one input has multiple outputs, I said a switch which turns on both light and tube light, then that is not a function. This log of 0 to the base 0 can give the value of 1, 3 and minus 9. And even if you take it mathematically, log of 0 to the base 0 is 1 and log of 0 to the base 0 is 3. Then hypothetically 1 should be equal to 3, and this is wrong. So hence we come to the fact that a should not be equal to 0. Now another concept, why did we take a should not be equal to 1? Suppose we take the a value to be 1. This was a is equal to 0. Now if we take a value as 1, then what happens? We know that 1 to the power anything is equals to 1. Let us take 1 to the power 3, it gives us 1. 1 to the power 9 gives us 1. 1 to the power 7 gives us 1. 1 to the power minus 3 gives us 1. So any value of 1 gives us 1. If I try to write this in the terms of logarithm, log of 1 to the base 1, this is equals to minus 3. If according to this, log of 1 to the base 1 is equals to 9. According to this, log of 1 to the base 1 is equals to 7. Again the same issue arises over here. One input has multiple outputs. One function has multiple outputs. Then that is not a function. So hence, according to this, minus 3 would be equal to 9, and that is not possible. So this is also one area where a conflict arises. That is why the value of a should be greater than 0 and not equal to 1. This can also be written as a should be 0, infinity and not equal to minus 1, or 0, 1, then 1, infinity, not 1, close to 1. So it should not be equal to 1 and should not be equal to 1, infinity. So this is how we represent it. So usually the basic idea is the value of a, that is the value of base, can be equals to anything greater than 0 but not 1. And what if we put negative? Then also it becomes not defined. And logarithm is only defined for positive values and for positive terms. This was the property. Now, according to the properties of logarithm, log of x to the base x is equals to 1. Log of x to the base x is 1. It means that when the base and the power, when both are same, when the base and the term, when both are same, then the logarithm value is 1. How can we say that? 1. So 2 to the power 1 is equals to 2. 4 to the power 1 is equals to 4. 5 to the power 1 is equals to 5. If I try to take the logarithm of this value, how will we get it? This will be log of 5 to the base 5, that is equals to 1. So hence log of x to the base x is equals to 1. This was the first property. Second property is, for that we have to assume another idea. We know anything x to the power 0 is equals to 1. If we take 3 to the power 0, that is 1. If we take 9 to the power 0, that is 1. If I try to express this in terms of logarithm, what will I get? Log of 1 to the base 9, 0. If I try this again, log of 1 to the base 3 is equals to 0. So what we can assume from here is, now see, there are another conflicts that two functions are given, or two different inputs are giving the same output. Is that a function or not? Yes, that is a function. So it means that there are two buttons and they both are linked to a single answer. Then that is correct. If you press this button, then the fan turns on. If you press this button, the fan turns on. That is correct. A single input should have a unique output. A unique input should have a output. So hence we can say this is a function. Log of 1 to the base 3 is equals to log of 1 to the base 9, that is equal to 0. So many inputs should not have multiple outputs. A single input should have single output. It is in that terms. So we can define this as a function. So the second property is log of 1 to the base x is equals to 0. Always. This is also a common term. Now coming on to the more important and more interesting formulas, or the more interesting properties. First interesting property is log of mn, that is equals to log of m plus log of n. This is the product rule, or the product rule of the logarithms. Now here we have to know that the base is common base. If you have any multiple in logarithms, then they get added. Suppose we have log 9, then this log 9 can be represented as log of 3 into 3, and using this property we can say this as log 3 plus log 3. Now if you remember this logarithmic values, we wrote that log 3 is equal to 0.48, and we also wrote that log 9 is equals to 0.96. From how did we get the value of log 9? If you use this term, you will get the value of log 9. So that is 0.48 plus 0.48, and that is equals to 0.96. And this is the value of log 9. So actually we need to learn only the value of log 1, that is 0. And yes, also one more thing. We learned that log 1 is 0. And log 1 to the base, what did we have here? We had 10. And according to this property, log 1 to any base is 0. Hence the value of log 1 is 0. Now we are understanding how did we get those values. Log of 1 is 0. Log of 2 is 0.48. This log of 2 value we have to remember. We have to remember log of 2, log of 3, log of 5 and log of 7. Not even 7. 7 is the inverse of 3. So from log of 3 value, we derived the log of 9 value. This was one property. Now there is also a derivation for this property, wherein we have to assume, for that we have to take one more property. Before moving on to that, we have another property, that is log to the base a m by n. This is called the division rule of logarithm. That is log to the base m minus log to the base n. This is also a same property, similar to this actually. Here in the terms of multiplication we have to separate and add them. In the terms of division we have to separate and subtract them. Then one more we have, that is log of x power n to the base a. This can be written as n into log of x to the base a. How can we represent this? To represent this, let us take the value of log 2 and log 8. Log 2 value is 0.3 and log of 8 value is 0.9. We know these two values. Now how do we use this property to get to this value? So we can say that log of 8 is log of 2q. We can ignore the bases because it is a common base everywhere, that is base 10. So log of 2q. Now using this, if we use this property, then we will get 3 times of log of 2, that is 3 times of 0.3, that is 0.9. This is the log 8 value, and this is what we actually found out. This property has a very good derivation. How do we derive this? This log of x to the power n can be written as log of x to the power n, that is equals to log of x into x into x into x into x. How many times? N times. X into x, how many times we have it? N times. Why? Because it is x to the power n. Now using this rule, which rule? Multiplication rule, we can say this as log x plus log x plus log x multiple times. How many times? N times. So we can say this as n times of log x, that is n into log x. This is the actual derivation. So how do we get log x to the power n? So x to the power n means multiplying x n times. This multiplication of x n times, using this formula log of mn, we can write it as log x plus log x plus log x m times. Now n times addition, we can take common out. After taking common out, we get n into log x, that is n log x. This was the derivation for this formula. After this we have log of 1 by x. This is equals to log of x minus log x. How is this derived? It can also be derived as log of 1 by x. Using this formula, division rule, we can say this as log 1 minus log x. Log 1 value is 0, so that will give us minus log x. This was the derivation of this logarithm. Now these were the very important and the main properties of logarithm. Using this we can solve many problems. Now there is one very important, very unique question, that how will you find the logarithm of 2.5? Now this question can be solved using multiple methods, but the actual method or the easiest method is making this in the form of 25 by 10. After making in the form of 25 by 10, we can cancel out by taking the common. So log of 5 by 2. So this will give us log 5 minus log 2. The value of log 5 is 0.7 and the value of log 2 is 0.3, that is 0.4. This is the answer to the question of log of 2.5. So these types of questions are very common as a part of a problem in physics or mathematics. So this was all about the properties of logarithm. Now for derivation of this, we are taking, suppose we can try to derive the derivation of this one as well. We know that we can take an example of x is equals to log m to the base a, y is equals to log n to the base a, and z is equals to log mn to the base a. Now after making an antilog of this, we can say this as it is just like a power x is equals to m. From here we can say that a power y is equals to n. From here we can say that a power z is equals to mn. These are the three values. What did we do here? We supposed a variable x is equals to log a to the base log n to the base a, y as log n to the base, and z as log mn to the base a. Then we took the antilog. Now after taking antilog, we see that m and we have the terms m, n, mn. Okay, if we multiply m and n, we will get mn, right? So what we are doing is we are multiplying a power x into a power y. After multiplying this, what do we get? We get a power xy. A power xy is actually taken as z. How it is taken as z? A power xy, that is taken because a power m into n is equals to mn. So m is taken as a power x, n is taken as a power y, and mn is taken as a power z. Now the bases are equal. So x, y is equals to z. what is x? X is log of m to the base a, y is log of n to the base a. So log of m to the base a into log of n to the base a. This, when multiples are added, then we add the powers. So we get here at x plus y is equals to z. What is x? Log of m to the base a. Plus what is y? Log of n to the base a. And what is z? Log of mn to the base a. This is the derivation of the formula. Now how do we derive this formula? We took x as a value of log of m to the base a. We took y as the value of log of n to the base a. And we took z as a value of log of mn to the base a. Now after taking antilog, a power x is m, a power y is n, and a power z is mn. Then we see that m into m is equals to mn. And m value is a power x, n value is a power y. A power x into a power y. And mn is actually a power z. When the bases is same, we add the powers. So a power x plus y is equals to a power z. We can cancel out the a's. X plus y is equal to z. Log m to the base a plus log n to the base a is equals to log m into the base a. This is the derivation of this property. We can derive this property as well as the same. We can take the same x, y and z, and this time instead of doing m times n, what we can do is we can do m by n. Here we will do m by n is equals to mn, suppose like m by n. What is the value of m? That is a power x by a power y. That will become is equals to a power z. So a power x minus y is equals to a power z. X minus y is equals to z. And here z is actually log m by n. We have to assume that. So x is log of m to the base a minus log of n to the base a is equals to log of m by n to the base a. This is the derivation of this formula, division. So I hope you have understood the topic till now. This was the main basic introduction to what is logarithm and the main concept of logarithm. So we understood what are the properties of logarithm, what is natural log, what is common log, how to convert them, and what are the main values of logarithms. Now using all these properties, we can solve or we can derive all the values of logarithm. So I hope you have enjoyed today's video. This logarithm concept is used in chemistry, mathematics, physics and many other topics as well. So I hope you have enjoyed this. See you next time in the next video. Thank you and goodbye.